on only the which which allows only steep potentials within the within the quantum gravity, and we know that the flat potentials plays an important role in the model building for the inflation in dark energy. So now moving to the Bangjak's like our work. So there so in 2007, Georgie came up with the idea of the unparticles. The idea is that that the physics beyond the standard model, there may be a may be a sector that is conformally invariant in the infrared region, and the classically scale invariant in the ultraviolet region, that we call as an unparticle sector and the Bank sector respectively. And these sectors uh, are are characterized by the scale of scale of dimensional transmutation lambda mu. So now we will move to the thermodynamics of the unparticles. So one can write the energy momentum tensor of any gas theory in terms of the beta function, and we know that the beta function vanishes in the conformal limit. Now one can perform the thermal average of the energy momentum tensor. One gets that one gets that the energy momentum of the beta function of the gas theory is proportional to the beta function, which in turn is proportional to the temperature of the gas theory to the anomalous to the power of anomalous dimension. And now one can use the laws of thermodynamics in order to get the energy and pressure of the unparticles. Here we can see that that the energy and pressure of the unparticles take a small correction to the regular radiation part, which can be which these corrections can be small or large, taking the values of delta and t. So now coming to the cosmology consequences with the unparticles, we will be working with the FRW background. So within the FRW background, the energy, one can write the continuity equation for the unparticles. So using the continuity equation, one can directly solve the continuity equation, and can get the scale factor that is a function of temperature. Here temperature is T is the temperature of the unparticles. This looks a bit messy, but it can be simplified by using a dimensionless definition of temperature that is defined as the ratio of the T divided by Tc, where Tc is defined as the summation of the energy density. Sorry. Summation of the energy density and pressure. Pressure. So now using the convention, one can write scale factor in a nice nice form. So now if one demands Tc is real and positive, and also one demands the positivity of the energy density at the critical temperature, then there is a extremum of the temperature, and this extremum ensures that there is a digital expansion. So now first we will discuss about the bouncing solutions that emerge from the that can be generated from the unparticles. So we first consider the universe filled with only unparticles. So now if one wants to get the bounce, so one requires the energy density and the pressure should be 0 and the negative respectively, and by like choosing demanding such conditions, one can constrain the unparticles parameter b and delta in such a way. So here is the example of the example of the bounce with unparticles only. Here the left panel shows that how the Hubble parameter evolves throughout the evolution, and while the right panel shows the evolution of the temperature. So now we know that the unparticles can be used as a mechanism for the generating a bounce. So for the realistic scenario, one can use unparticles on the top of the perfect fluid, and choosing perfect fluid, one can get interesting cosmological scenarios. So we will be adding a perfect fluid that with having equation of state W. So now, as we know that the a perfect fluid energy density varies as the a raised to minus 3 1 plus omega, and we know that the from our from the previous slides, like, that the scale factor is proportional to the temperature. So now energy density of the energy density and pressure of the perfect fluid can be expressed in terms of the temperature of in the function of a temperature only. In this way, one can express only all the dynamical quantities in by only using temperature. And also considering unparticles plus fluid offers a rich phenomenology. Here T0 is a temperature at the bounds, and where alpha is a gauge parameter which tells the how much unparticles we have compared to the perfect fluid. And at the t equal to 0, one can have bounce recoillapse of the scale factor, and to give an idea of the what kind of cosmological scenarios we can get. Here is the phase plot that where the x-axis is the equation of state of the perfect fluid, while the y-axis is the anomalous dimension delta of perfect of the unparticles. Now here the green, yellow, red, brown corresponds to the bounce with maximum of temperature at the bounce with minimal of temperature, recollapse, and the recollapse with maximum temperature. And the numbers from 1 to 6 corresponds to the different cosmological fates, such as for example, uh, reason 1 shows the cyclic scenario, where here it's shown in the left panel. As we can see that the scale factor and temperature are collapsing and bouncing back in each cycle, and it happens for the infinite times, while the region 4 corresponds to the normal bounce, which we can see the right panel of the figure. Here we can see that the Hubble parameter starts is contracting, then it goes to the a finite value of a scale factor, then it again bounces back and expands forever. So till now we have only found the bouncing scenario. Now we'll look for the another application of the nanoparticles, that is for the for the dark energy purposes. So we have already mentioned that there exists a pole of scale factor. So now it's not new in cosmology. A well-known example is radiation. So in the same way, we have also a temperature that is critical temperature, where so there are two possibilities. If temperature of particles is below than the critical temperature, then we have a digital bounce that we already discussed. And if temperature of particles is higher than the critical temperature, then there's a possibility of the dark energy. And there is no way of crossing the temperature. So now um, let's see the condition. What condition should be on the parameters, so that we can get a dark energy model from the unparticles. So first thing, that critical temperature should be positive, and also the energy density at the critical temperature should be also positive, and the temperature must always decrease while the scale factor grows, and the null energy condition should be obeyed throughout the evolution. So now we will see the evolution of the particles in early and the late times. So in early times, when the temperature is much larger than the critical temperature, then the unparticles correction that is proportional to the b times t raised to 4 plus delta is negligible, and unparticles act as regular radiation, and effectively universe is filled with radiation and dust. While in the late times, evolution of the temperature and energy density And the equation of state is given as following. So here one can see that the energy density and the equation of state of unparticles is is uh, is like is the constant plus some decaying term that is very similar to the cosmological. So now in this slide, the dynamics of our model in left panel, I'm comparing the evolution of the parameter density parameter of each fluid between lambda CDM and the unparticles, while the while the right panel shows the equation of state for the universe throughout the evolution. As we can see here, that the lambda CDM and unparticle dark energy is like um, are matching at like very high precision. So there is no way to distinguish at the background level. Now, as I want to mention here that the delta that there are two parameters on particles, delta and y0. The background dynamics is not depending on delta. While there is a dependence on y0 that can be fixed from the imposing BBN of semi constraints. So left panel shows that shows that the parameter space where the BBN constraint are satisfied, while the right panel shows the BBN parameter space where the BBN CMB constraints are satisfied.
3 minutes.
So now in order to distinguish the our model to the lambda CDM, so that it can be falsified in future coming experiments. So we use perturbation theory to calculate the growth index for our model and compare to the lambda CDM, and we see that there is significant difference from the lambda CDM, and that can be detected in the future experiments. So now the last question that I want to address, that our model can resolve that the Hubble tension is the conflict of the value of the Hubble tension measuring from the different observations. So addition of the Hubble parameters like pushes the Hubble tension to the 2 to 3 sigma, as it pushes CMB derived Hubble parameter towards 70 kilometer per megaparsec per second. So now I'll summarize my talk. So conclusion from the bouncing scenarios. So unparticles can be a possible mechanism to generate the bounce, and the unparticles filled with if a universe filled with unparticles is a de-Sitter for the unparticle on top of the perfect fluid, which gives rise to the rich phenomenology. One can get different kind of cyclic scenarios. For the conclusion for the dark energy, one can get the like there is a unparticle behaves the radiation in high temperatures, and the dark energy for the low temperature. This model is consistent with the lambda CDM at the background level, while it shows significant difference at the level of perturbations. And dark energy avoids swamp-land conjecture without modifying gravity, as also it also solves the cosmological constant problem, also the coincidence problem, and addition of the particles resolves the Hubble tension. Thank you for listening.